Today we're going to begin looking at probability distributions. Everything that we've done so far has been setting us up to be able to explore this topic. So let's talk about this kind of in an introduction to what are probability distributions and what can we do with them way. So in this section we're going to learn about what random variables are. We're going to talk about the idea of a probability distribution, probability histograms, and we'll talk a little bit more about what it means to be significantly low or high, and of course finding like the mean and standard deviation, variance, things that we might want to know about these random variables from these probability distributions. So what is a random variable? Well, a random variable is a variable, a lot of times we use x, but it could be y, any variable name, all right, that has a single numerical value determined by chance for each outcome of a procedure, all right? So rolling a dice, the number that comes up on the dice, that is a random variable, all right? So let's talk probability distribution. What's that? Well, a probability distribution is a description that gives the probability for each value of the random variable. So a lot of times it gives us this format as a table or a formula or a graph. And any of these three ways is an acceptable way to see a probability distribution, and we should be able to deal with all of them. Probability distributions and random variables can be either discrete or continuous. When we say it's discrete, it has a collection of values that's finite or countable. All right. What it means for something to be countable means that you could assign a number to it and potentially count them all if you had infinite time. So there might be infinitely many values, but in theory at least, you could count them all if you had enough time. All right. So when we're looking at tossing coins and counting how many heads we get, that's an example of a discrete random variable. Rolling a dice is discrete random variable. Our other option is that it's a continuous random variable. Continuous random variables have infinitely many values. So this is the idea where if you take two values, you can find another one in between, and then you take that one and another value, and you can find one in between, and there's always more in between to have. All right, that's a continuous random variable. So it has infinitely many values, and we can't ever count the number of values. Even if with infinite time, you couldn't really think about counting them all. So examples of this would be body temperatures, heights, weights. All of these things have infinite potential values, and we couldn't possibly count them. Right. So what does it take to make a probability distribution? We have these different types of random variables, the discrete and the continuous one, and we can make probability distributions of either one. So what makes a probability distribution a probability distribution? There's three things. So the first is that the variable has to be a numerical variable. It's not a categorical variable. So remember, categorical variables are things like colors or labels on things. So numerical value, all right? So we have our numerical random variable, and each one of those values that our variable can take is going to be associated with some probability. Now, we also, our second requirement is that the sum of all of those probabilities has to be 1. Small caveat there that sometimes rounding happens and messes us up a little bit for it to be exactly 1, but it has to be so close to 1. So if we have probabilities like 0.999 or 1.001, we're not going to get like super excited about that. But that's our goal, is to have the probabilities all add up to 1. Our third and final requirement is that each of the probabilities needs to be between 0 and 1. So the probability of any single value of the random variable has to be between 0 and 1, and that's inclusive. They could be 0 or 1 for some of the values. So let's take a look at an example. A coin toss. So we're going to be tossing 2 coins, and we're going to be looking at the random variable x, where x is the number of heads when 2 coins are tossed. So x is a random variable because its numerical values depend on chance. It's a discrete random variable because the possible outcomes are 0, 1, and 2, as we see there. And we can even find the associated probabilities. So here's our 3 requirements that we need to check. It's a numerical random variable. Its values are associated with probabilities. We're good there. The sum of those probabilities, the 0.25, 0.5, and 0.25 is 1, so we're good there. And each of those probabilities, each of those individual probabilities is between 0 and 1, so we're also good there. All 3 requirements are met, so we have our discrete random variable with these 3 possibilities, and this is our probability distribution. So a probability histogram, it just graphically shows us our probability distribution. Notice it's a lot like a relative frequency histogram. If we had taken a relative frequency histogram and labeled the vertical axis with the decimal forms of percents rather than percents, and we had used theoretical probabilities like the along the way instead of like looking at like the actual results that we got when we did the experiment, then we would have a probability histogram. So here's the probability histogram for the number of heads when 2 coins are tossed. You can see that at 0 and 2, the probability is 0.25, as the height of that bar is 0.25. And for 1 head, the probability of getting 1 head is 0.5, because the height of that bar is 0.5. All right, so we've seen the graph now, we've seen the table. The last thing that we could, or last way that we could show a probability distribution is through a formula. So here's the formula, P of x, that's going to actually give us the probability distribution that we've been looking at. We get it by taking 1 divided by 2 times the quantity 2 minus x factorial times x factorial. Now remember, 0 factorial is 1, so if we plug in 0 for this, we get 1 over 2 times 2 factorial times 0 factorial, which is 1 over 2 times 1 times 1, or 1 over 4, which is 0.4. And we can do this for 1 and 2 as well, and we'll get this probability distribution that we had. So we should be able to find the probabilities if we're given a formula. We should be able to find the probabilities if we're given a graph, and we should be able to find the probabilities if we're given a table. Constructing the table and constructing the graph are not too difficult to do. Figuring out what the formula should be is a little bit more difficult, so we're setting that aside for now. Don't worry about it too much, all right? So, an example. Here we are. Job interview mistakes. So, hiring managers are asked to identify the biggest mistakes that job applicants make during an interview. Tables based on their responses, and we want to know, like, does this describe a probability distribution? We have a table, so that's one of the ways that we can describe a probability distribution, but does this actually do that? All right, so looking at this, the values that x takes are a bunch of words, so it's not numerical data. And when we look at the sum of the probabilities, It's 1.57. It's not 1 or anything that could have been rounding errors different from 1. Each of the values that x takes on is assigned a probability though, so it's got something going for it. But at the end of the day, because the first requirement fails because it's not numerical random, it's not numerical values, they're categorical instead, and because the sum fails to be 1, then it is not a probability distribution. All it takes is one of those 3 criteria failing for it to not be a probability distribution. Here there's kind of overkill by 2 of them failing. Right. So if we have a probability distribution, we would love to be able to find out some things about it, like the mean, the standard deviation, the variance. Notice that probability distributions, when we talk about them, we're talking about the population instead of a sample, because we're talking about, like, in theory, what would the probability be? All right. So that's talking for the entire population rather than looking at some data from a sample and constructing this probability distribution. Since we're dealing with the entire population, we're talking in parameters, not statistics. So we'll be using those Greek letters to stand for the mean, the standard deviation, variance, rather than the x bar and s squared that we've been working with when we were dealing with sample means and standard deviations and variances. So here are our formulas. They look a little bit different, but also similar for what we were dealing with before. So the mean for a probability distribution, we find that by taking each of the values of our random variable and multiplying them times their associated probabilities. We do that for all the possible values of our random variable, and then we add them all up. And that's going to give us our mean of our probability distribution. The variance for a probability distribution is going to be found by taking each of the values that a random variable can take on, subtracting the mean from that, so we're finding the distance between the value of our random variable and the mean, and we're going to square that so negative stuff doesn't mess with us, and then we'll multiply it times the probability that's associated with it. We'll do that for each of the values that our random variable can take on, and we'll add them all up, and that gives us our variance. Right. There's another formula there for the variance that's a little bit easier if you're trying to punch things in your calculator potentially, but ultimately, like, conceptually what's going on with the variance, that first one that we just talked through, the better way to go. And finally, the standard deviation is the square root of the variance. So we find the variance. This is using that second formula, but you can use the first formula, it's fine. And you take the square root of it and you have the standard deviation. All right. So really quick, our Greek letter review, the mean is represented by mu, and our variance is sigma squared, and our standard deviation is sigma. All right. So expected value. The expected value of a discrete random variable is denoted by E. We use capital E. And it's the mean value of the outcomes. So it's what we might expect to happen. And since it equals the mean, we can use the mean formula to find the expected value. All right, so let's take a look at finding the mean, the variance, and the standard deviation in our flipping 2 coins example. All right, so again, this is the probability distribution that we had. So finding the mean looks like this third column here. We're going to take each of our values of our random variable, x, and we'll multiply them times their associated probability. So 0 times 0.25, 1 times 0.5, and 2 times 0.25. Once we do all of that multiplication, then we add them up, and we get a total of 1, and that is our mean. So our mean is 1, right? Then, if we want to find the variance, we can use that mean. We'll take each of our random variables, subtract the mean, square that difference, and multiply it times the associated probability. So we'll take 0 minus 1, square it, and multiply times 0.25. We'll do the same thing with 1, so we'll do 1 minus 1, square that, times 0.5. And we'll do that for 2, so 2 minus 1, square that, times 0.25. And when we do that, we get a variance of 0.5. So we have a mean of 1 and a variance of 5. If we want the standard deviation, all we have to do is take the square root of our variance, and if we do that, we get 0.707107, or 0.7 if we round to the 1 decimal place more than our data is. All right, so interpreting this, we would tell people, hey, like tossing 2 coins, the mean number of heads is 1 head, the variance is 0.5 heads squared. Notice our units are squared. And the standard deviation is 0.7 heads, all right? So the expected value, remember that was equal to the mean. So also the expected value of the number of heads when 2 coins is flipped is 1 head. All right, so if we were to collect data on a large number of trials of flipping 2 coins tossed, we would expect to get a mean of 1 head. All right, that's kind of like our expected value, what's going on there. All right, so range rule of thumb, this has not changed. All right, so things are significantly low if they are 2 standard deviations or lower below the mean. All right, so the mean minus 2 standard deviations, that's our like threshold for anything less than that's going to be significantly low. Same 2 standard deviations adding them to the mean, anything above that is going to be significantly high. And our values that are not significant are the things that are within 2 standard deviations of the mean. So if we take a look at our tossing coins, we found our mean was 1, we found our standard deviation was 7 or 0.7. So using the range rule of thumb, like, is it significantly high if we get 2 heads instead of 1? Well, the range rule of thumb says take the mean, add 2 copies of the standard deviation. So 1 plus 2 times 0.7, that gives us 2.4. And so significantly high numbers are going to be above 2.4. So 2 heads is not significant, all right? Not significantly high or low, all right? So that's where we are. So again, significantly high numbers of successes, if we take n trials, significantly high number of successes is if the probability of X or more successes is 0.05 or less. 0.05, again, is not necessarily the number that you have to go with, and depending on the context of the problem, we don't want to go with 0.05 always. Sometimes 0.01 is better, or 0.001. It depends on the context, all right? And similarly, significantly low, all right? It's finding a value that low or lower is less than or equal to 0.05 or 0.01 or whatever we're going with given the context. All right, the rare event rule of inferential statistics. So, if under a given assumption, the probability of a particular outcome is very small and the outcome occurs significantly less than or significantly greater than what we expected with that assumption, we conclude that the assumption is probably not correct. This probably looks familiar. We've talked about this before. Same deal with probability distribution, same rare event rule. All right, if we find this significantly less than or significantly greater than, we say, hey, you know what? Something about the way we were thinking, it's maybe messed up. All right, and just a reminder, expected value, same as the mean. So now let's take a look at another example using expected value. So let's be a better. So we have $5 to place on a bet at the Golden Nugget Casino in Las Vegas. And we've narrowed the choice to 2 bets. We're either going to play roulette and bet on the number 7. We're feeling good about that number for whatever reason. And craps, we're going to bet on the pass line in the dice game of craps. Those are our 2 options. All right. So let's figure out what our expected payout is if we take each of these bets to figure out how to bet our $5. So if we bet $5 on the number 7 in roulette, the probability of losing $5 is 37 out of 38. There are 38 numbers on the roulette wheel. 37 of them are not the number 7. And the probability of making a net gain of $175, they would give you $180, but 5 of that would be your $5 back, is 1 out of 38 because there's 1 7 out of the 38 numbers on the roulette wheel. So we want to find the expected value if we place the bet on the number 7 in roulette. Right. So if we do that, then the event options are we're either going to lose or we're going to win. All right. Losing corresponds to a random variable value of negative $5 because we have bet our $5 and we do not get it back. So we have lost $5, negative $5. Winning corresponds to a random variable value of $175 because they'll give us $180, but 5 of it came out of our pocket to begin with. So the probabilities associated with each of those values are the 37 out of 38 and the 1 out of 38. So to find the mean for this random variable, which corresponds to our expected value, we're going to take our random variable value, x, multiplied times our probability. So doing that for each of these, we get the numbers on the right-hand column of my table here. And then we have to add them up, and that's how we find our mean. So we get a mean of negative 26 cents, rounded to 26 cents, all right? So that means, interpreting this, it means that if we bet $5 on the number 7 at the roulette wheel, the expected value is that we lose 26 cents. Okay? So keep that in your mind, and then let's go back to our other option. Our other option was to bet $5 on the pass line in the dice game of craps. So the probability of losing $5 is 251 out of 495, and the probability of making a net gain of $5 is 244 out of 495. So if we bet $5 on the pass line and win, they're going to give us $10, but again, 5 of it came out of our pocket to begin with, so we're really only gaining $5 in that case. All right. So let's talk about our expected payout here. All right. So we are again losing corresponds to negative $5. We bet our $5, we don't get it back. This time winning corresponds to that net profit of $5 because they give us $10, but 5 of it was ours to begin with. So we only really gain $5. So again, to find the mean, we multiply across the x times its associated probability. And when we do that, we get the values in the right-hand column, with the exception that that second value, the $2.464646, should be positive. All right. So then we add them up, and when we add them up, we get negative 7 cents, or it rounds to negative 7 cents. So if we bet $5 on the pass line in the craps game, we can expect to lose 7 cents, an average of 7 cents. All right. So interpreting this, the $5 bet on roulette results in an expected value of 26 cents lost, and the $5 bet in craps results in the expected value of 7 cents lost. So because you're better off losing 7 cents instead of 26 cents, the craps game is better in the long run. Even though the roulette game provides an opportunity for a larger payoff when playing the game once. So if you're only playing once, maybe the roulette game is the way you want to go. All right. So ultimately, the best way to have the expected value of the most money at the end is to put the $5 back in your pocket.